Isotopic substitution changes NMR spectra by introducing or removing nuclei that interact with magnetic fields. So replacing a common nucleus like carbon-12 with carbon-13 makes new signals appear, alters splitting patterns, and can change relaxation times and signal intensities. When you swap an isotope that is NMR-active, like carbon-13, into a molecule, it becomes visible in the spectrum and can couple to nearby nuclei, causing extra splitting of peaks that did not exist when the nucleus was the NMR-inactive carbon-12. Think of coupling like little magnets holding hands across bonds. If one partner is invisible, the visible partner shows a single peak, but if both are visible, they make multiple smaller peaks. Carbon-13 is much less abundant than carbon-12, so its signals are weaker and sometimes need more scans to detect, and its different magnetic properties also change how quickly signals fade, which affects peak shapes. Isotopic substitution can also simplify spectra if you replace a coupling nucleus with an NMR-inactive isotope, removing splitting and making peaks easier to assign. Students often assume replacing carbon-12 with carbon-13 only adds a new peak, but it also creates or removes coupling that changes how other peaks look, so expect altered multiplets rather than isolated new lines, and the fix is to think about neighboring spins when predicting spectra. Another common mistake is ignoring intensity changes because carbon-13 is scarce, so peaks may be tiny unless enrichment is used, and the simple remedy is to increase scan number or use enriched samples. Some learners forget that isotopic substitution can change relaxation behavior and therefore line width, so when peaks look broader or narrower after substitution, consider relaxation effects and adjust experimental parameters. Visit www.gumballdegree.com to find more videos and resources on isotopic substitution and NMR.